Okay, welcome back to another exciting episode of Mr. McKelvey Reads Out PowerPoints. There are a couple of links in the information down below that will be taking you to the core practical videos. I recommend having a look at them because the core practical will definitely be assessed in your summer assessment. So we're going to start with a bit of wave basics. The idea of a wave is that they transfer energy and/or information without transferring any matter. So an example, or if I'm over here at point A and you're over here at point B, and I speak and I say something like, hi, then the wave will carry the information and the energy towards you, even though the particles of air that have been vibrating to make me say the word hi stay where they are. They're described as vibrations or oscillations. They mean the same thing. It just means an object moving around a fixed point. So even though they move, they don't travel. It is the energy, not the particles, that move from one place to another. And we can see this when we think about sound waves and water waves. So much like I said, the evidence for this is that if I was to eat a mint over here and say hi, you would hear me say the word hi using your ears. And yes, that's me trying to draw an ear. Actually, not half bad. Okay. What are your ears? But you wouldn't be able to smell the mint because the particles of air would stay around near my mouth. They wouldn't travel over to you. There's no such thing as a sound particle. And if I drop a stone into the middle of a pond, then this water will stay where it is, but there will be an energy wave moving out, a ripple moving out that pond. The water particles will oscillate. They will move around a fixed point, but they will not travel. So, water waves. Ripples are movements of water, oscillations of water in a set pattern as a result of something causing it to be disturbed, some kind of a displacement. Ripples are when water particles vibrate up and down. Now, if we had something like a duck, so this little red dot here that's moving up and down on this, if we had a duck that's sitting on some water, the duck would not get carried along the top of this wave unless it was trying to, unless it was surfing. It would just kind of bob up and down where it is. So it's evidence that if we put something on top of a ripple, if we put something on top of the water, then it just stays kind of where it is and won't get moved from one area to another. It's evidence that the particles aren't moving, but the energy is. Similarly, for sound waves, if you hit a drum, you'll make a sound wave. The sound wave travels to your ear and you hear the drum sound. Sound waves cause air particles to vibrate back and forth. Look at an individual one of these red dots. That little red dot there is moving forwards and backwards, but is not actually traveling from point A to point B. So it's moving, but not traveling. The air particles do not travel from the drum to your ear. Only energy is transferred and not the particles. And there are two kinds of waves. We can call them transverse waves and longitudinal waves. In a transverse wave, the particles within the wave move perpendicular to the direction the wave is traveling. What does that mean? Well, this wave is moving from point A to point B. This wave is transferring energy and information from point A to point B. And the particles are vibrating up and down. If we draw a line between those two lines, we can see that there's a 90-degree line in between those two. If we flick a rope up and down, or if we flick a slinky up and down, we can see that the energy is being transferred along that slinky or that rope, but the particles themselves are not. Now you need to know examples. Water waves, electromagnetic waves, so anything from the EM spectrum, radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, and gamma rays, all of those things are EM waves, and guitar strings or ropes. Longitudinal waves are compression waves. Compression just means to squash something, where the particles are vibrating in the same direction as the wave movement. We say that they're vibrating parallel to the direction that energy is traveling, or to the direction that the wave is traveling. So again, my wave is going from point A to point B. The wave motion is from left to right, and the particle motion is from left to right as well. These two lines are parallel to each other. This is the wave produced when a spring is squashed and released. Examples of that, sound waves and a type of seismic wave. And seismic waves just refer to earthquakes. So it's the particles and the waves that are moving. Particles and waves are moving, but the energy and the information is traveling from point A to point B. Now, there's some parts about waves that we have to know as well. So you have to be able to confidently label these wave diagrams. So wavelength, fairly self-explanatory. It is the length of one wave. Now this wave will start here. Displacement means how far away from the original place they are. So this is Bob, and Bob takes one step to the right, one step to the left, another step to the left, and another step to the right. Bob has taken 4 steps, but he has only been displaced by 1 step. The maximum distance Bob moved away from where he started is 1 step length. If this was a particle that was vibrating up and down like a water particle, then my water particle has moved up to this maximum displacement and has moved down to this maximum displacement. But at 0, at this point here, it hasn't moved at all. The length of a wave starts at 0, it's moved up, it's moved down, and then it goes back to where it started again. That is one complete wave. So in this picture, that's 1 wave, that's 2 waves, and that's a 3rd wave. We can measure the wavelength from peak to peak, but when we're counting waves, it's good to start at the start and see how many there are, because it looks like there are 1, 2, 3 waves here. That is not the case. We have got 2 and a half. So if you're calculating wavelength, you just measure from the peak of one wave to the peak of another, or the trough of one wave to the trough of another. And I'll label this, and you can pause if you want to, but I'm just about to get rid of all of this writing. Now, amplitude is the maximum displacement of a point in a wave from its undisturbed position. What does that mean? I have to imagine my particle is here. It has vibrated up, it has vibrated down. The amplitude is the maximum displacement of a point of a wave from its undisturbed position. Its undisturbed position is here, on this line, where there is 0 displacement. So the amplitude of this wave will be there. Now, because the positive and negative vibrations on a wave are the same, if everything else is equal, then the amplitude is just the distance from the center, this line in the middle of the waveform diagram, to the maximum point it moves. Frequency is a number of waves passing a point per second, and we can see that in a graph as well. And we said that we had 2.5 waves here. To find out the frequency, we need to know the amount of time this has taken. So we can have a look here on this axis, on the x-axis, and let's just say that from here is 0 seconds and here is 1 second. If I have got 1, 2.5 waves, that means I have got 2.5 waves per second. That is the same as saying a frequency of 2.5 hertz. I told a joke about frequency. It's really funny. You'll laugh so much that it hurts. LOL, which is lingo for ha ha ha. The period is the time taken to produce one complete wave. So again, in this example up here, we have got 2.5 waves per second. If I want to find the period, I need to know how long it takes one wave to complete its full cycle. The equation for this is that the period is 1 over frequency. So I divide 1 second by the frequency of the waves. The period for this wave is 0.4 seconds. This wave will complete itself in 0.4 seconds. This wave will complete itself in 0.4 seconds. Now, this diagram can also refer to a longitudinal wave. The displacement of a transverse wave is described as peaks and troughs. What does that mean? The displacement is described up here as a peak and down here as a trough. But the displacement in a longitudinal wave, they're called compressions and rarefactions. Places where the slinky is close together and places where the slinky is spread apart. Make sure we know these because it's a very common multiple choice short answer question. Now, there are two equations. You don't need to recall them. They will be on your equation sheet, but you do have to use them. Wave speed is the speed at which the energy is transferred by the wave, or how quickly the wave moves through the medium it is traveling in. Now, you will often see this written down as wave velocity. Quick reminder, if you move from point A to point B in a straight line, the meters per second that you do that, if it is in one continuous direction, is the velocity. If you change direction multiple times to go from point A to point B, then that is considered as speed. Velocity, v, is a scalar. Velocity v is a vector. Speed s is a scalar. Now we can say wave speed because wave speeds tend to travel in one direction. They can be bent by refraction, but for the most part, they just travel in straight lines. Make sure that we know the units, meters per second, hertz, and meters, and seconds. So here's a nice example of a wave that's moving. You can see that this is a waveform diagram tracking the movement of a particle. Just so you know, the amplitude of this particle is 1. The maximum displacement is 1. If I wanted to measure the wavelength, I would have to measure from tip to tip. What would the distance of that be? And if this was seconds, I just have to count how many waves there are in this amount of seconds, and then I'll be able to find out the frequency. I can then find out the period by doing 1 over f. Look at a question that looks like this. There's a frequency of 0.5 hertz and a wavelength of 6 centimeters. Let's find the answer. This is important. We always want to go to our base units. 1 meter is the same as 100 centimeters. How do I go from 100 to 1? I divide by 100. How do I go from 1 to 100? I multiply by 100. So how do I go from centimeters to meters? I divide by 100. How do I go from meters to centimeters? I multiply by 100. That's why this number here is 0.06 meters and not 6 centimeters. Let's say this was a 2-mark question. You would get 1 mark if you did 0.5 times 6. You would need 2 marks to realize you needed to convert that unit down to its base unit. And there's the answer, 0.3 meters per second. Have a go of this. There's no special units to do. But notice that we have to use a different equation. We either have to use v equals f lambda, this letter is lambda, or as my year 9s like to call it, sheep daddy, lambda, which I find absolutely hilarious. It stands for the wavelength. So lambda is the wavelength. Here's your answer. We have to have a couple of methods. We have to have a couple of practicals for measuring the speed of sound in air. So here's an example of where we might be able to measure the speed of sound in air. The cannon fires and the stopwatch has started. Now, we know about thunder and lightning. What do you see first, the thunder or the lightning? We see the lightning first because it travels at the speed of sound, which is about 300 million meters per second. Light travels 300 million meters per second. Sound travels at about 330 meters per second. So the reason why the thunder is just the sound of lightning. You see the lightning flash, and then you hear the thunder a period of time later. So when the cannon fires, you first see the flash. Start your stopwatch. The sound wave will propagate through the air, will go through the air, and when the sound wave reaches your ear, stop the stopwatch. That will give you the time between the flash and the bang. And if you know the distance that you are away from the cannon, then you can find out the speed of sound in air. So the cannon fires, the stopwatch is started, you can see the flash of light, which takes almost 0 time to travel 100 meters. When the sound reaches the observer, the stopwatch is stopped, the time was 0.3 seconds. This will give the time for the sound to travel 100 meters. Now in a previous video, we spoke about the fact that human beings' reaction time was 0.2 seconds to 0.9 seconds. So this isn't going to be very accurate. We'll only have finished starting the stopwatch by the time sound gets to us because 100 meters is too close a distance. So we can either use 2 microphones connected to a data logger. So if I put a microphone here and a microphone here, the microphone would pick up the sound and it would tell my data logger I picked up the sound at time A. And when the sound reaches this other microphone, it would tell the computer that we picked it up at time B. Computers have got no reaction times, so this would be far more accurate. We can't just say that it's more accurate, we have to say why. So it's more accurate because no reaction times. I mean, it's also fair to say that not many of us have cannons. So we might not be able to measure the speed of sound using a cannon. We might have to use a speaker and a couple of microphones. So two ways to improve this experiment. You can either go for longer distance. You can move it to maybe 500 meters so that you've got time to start and stop the stopwatch, or you can use a microphone and data logger. How do we measure the speed of ripples on a water surface? We use something called a ripple tank. Now, if you haven't seen one of these, make sure, please, that you come and ask either Mr. Patrick, Miss Calvert, or myself to show you one, because it's vital. A ripple tank is used to make waves, which are seen under the glass tank. Oh, also, there is a video for this. It'll show you in more detail. I'm just talking through it. I'm going to go through it quickly, so don't worry about it. If you don't understand it, there's a video in the information down there. I don't know what it's called, information area. You can follow that link, and it will show you this core practical. I reckon this is going to come up. Make sure you know it. So a ripple tank is used to make waves. A strobe light has a frequency of flashes adjusted until the wave appears stationary. This is the frequency of the water wave. So if my strobe is flashing on and off at a frequency of 12 hertz, and it means that the waves that have been projected either onto a screen up here or onto the table down below appear stationary, then I know what the frequency is. I can then measure the wavelength of the water wave using a ruler. So I just put my ruler down here, it's shown in this diagram here, and measure the distance between a light area and a light area, or a dark area and a dark area, whichever one is thinner. That will give me my wavelength, because it's literally the length of the waves being projected onto the screen. We convert it into meters and find the wave speed using frequency by wavelength. You could also, if you've got an incredibly large tank, follow a single ripple across the water, but because it goes very fast, it's very unlikely that you're going to be able to do that. Try the answer, try the question, and ignore that. It's not only higher tier. This is an old PowerPoint. This is a big fat lie. Ignore it. Here's your answer. Hopefully you got it right. There was nothing to convert, so it should have been a fairly straightforward question. Remember, you can substitute first and then rearrange, or rearrange and then substitute. Whichever is your preference, I don't care which, as long as you show you're working out for both. And always, 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 always write the equation that you're using. Because if you do make a mess up down here, we can give you benefit of doubt marks sometimes if we can see what you're working out was. Here's another question for you to try. Now, this is a bit of a cheeky one because we've got a ship that's up on the top of the water, and down here there is a shrimp. How does one draw a shrimp? I should be able to do this with my marine biology-ness. Do you know what? That's not half bad. Huh! I'm going to make it a happy shrimp. Look at that. So, the pulse of ultrasound takes 0.75 seconds to travel from a fishing vessel to a shoal of shrimp in the sea. The speed of sound in air is 1,500 meters per second. Now, yeah, cheeky. You don't actually have to divide this by 2 because they've given you the time it takes to go from there to there. What they'd usually say is a pulse of ultrasound takes 0.75 seconds to travel from a fishing vessel to a shoal of shrimp in the sea and back again. So it would take 0.75 seconds because what ultrasound does is it sends out a ping, it bounces off of something, and then there's a recorder that hears the sound at the end. You didn't have to divide by 2. This answer is wrong. That should be 0.75 seconds. That should be 0.75 seconds. And that answer, I assume, is going to be doubled. I don't know. 1023 or something. I don't know. Use your calculator. If you get a question about any kind of an echo, you could also get someone shouts, lol. They start a stopwatch, they shout lol, the sound waves go through the air, hit a wall and bounce back again. They start the stopwatch, and then they end the stopwatch, and there was 4 seconds of time in there. The distance from here to here was, say, 100 meters. What is the speed of sound in air? Well, it takes 2 seconds for the sound to go from the mouth to the wall and 2 seconds for the sound to go from the wall to the mouth. So rather than doing 100 divided by 4 seconds, you would do 100 divided by 2 seconds because you have to take the echo into account. In this question, you don't have to do that, which is why I'm all confused, but I'm going to leave that there. Let's put this down as a confusing moment. Move on. We can also talk about sound waves changing medium. We can do this for sound waves and for light waves. It's all really the same thing. And remember, medium just doesn't refer to the middle of small and large. Medium is just another word for something that a wave can travel through. So the medium that I'm talking in right now is air. If you wanted to go swimming, the medium you'd be swimming in is water. When waves travel from one medium to another, the frequency remains the same, because frequency is a property of the object producing the sound, not the medium it travels through. What does that mean? It just means the amount of waves per second will not change. It's a property of the thing that's making the sound, not the medium it travels through. But what will happen is that the wavelength will change. So this has got a really short wavelength, really high frequency. This will have a longer wavelength, and the frequency will stay the same. But the wavelength will change because sound will travel slower in air than water. And because it's speeding up when it goes into water, the wavelength has to change. So if velocity is equal to frequency times wavelength, if I reduce my velocity and my frequency has stayed the same, then my wavelength also has to reduce, otherwise the maths don't work. If the frequency remains the same, as velocity increases, the wavelength must also increase proportionally. Remember, proportionally starts at 0, linear trend. Y-axis, x-axis. When a light wave hits a boundary, they can be reflected, absorbed, or transmitted, depending on the substance they strike. So reflection is where it bounces off. Absorbed is where the ray goes in and doesn't come out again. And transmitted is when the ray of light goes through. Refraction is slightly different. It's when light, when it goes from one medium into another at an angle, bends. And we can talk about this specifically with electromagnetic waves. Refraction of EM waves occur when wave changes speed, when wave speed changes. Because the wave changes speed when it enters a substance of different optical density. Okay, so optical just density, think about it as just normal density for the sake of the GCSEs and just for now. What's more dense, air or glass? Well, glass, which means light will travel faster through air and slower through glass. The light wave will only refract if one side of the wave strikes the new material before the other one. Because remember that waves aren't just made of one little line, they are made of a multitude of lines all going in the same direction parallel to each other. So when that hits a surface at an angle, this ray will hit the surface first, this ray will hit the surface second, and this ray will hit the surface third, causing them all to slow down and change direction at different rates. The amount of refraction is different for different materials of optical density. That just means density for the sake of it now. And different wavelengths of light are diffracted by different amounts, resulting in a spectrum of color being produced when white light is refracted or dispersed by a prism. Diffracted should have said refracted. And here are the questions. So, little cat's feet, pause, haha. Little dog feet, pause, do the questions. Pause and try the question again. And here are your answers. All right, I'm just going to spend a couple of seconds going over the thing that was confusing me. We're going to do the shrimp boat thing, all right? So ultrasound and sonar work by sending out what's called pings. And a ping is just a big burst of sound. It sounds a bit like ping. That's why it's called a ping. Now, if I'm looking for a fish, I'm not going to draw a shrimp again. Sad fish because he's about to get caught. Poor little gill. If I'm looking for a fish, I can't see down into the water. But what I can do is send a ping of noise down. The wave will travel through the water, and when it hits this object, it will bounce back up. So a sonar is made of a ping maker, a big loud noise maker, and then some kind of a microphone. So I send out a ping of sound and I listen for the echo. I know that the speed of water, let's just make it easy. The speed of sound, let's just say it's 300 meters per second. It's not, but we're just going to say that it is. If my ping goes down for 1 second and I hear my echo after another second, I can figure out the depth of the fish. So if I have a ping sent out and then I hear the echo, if there's 2 seconds of time between the ping and the echo, I can work out the distance away that that wave has traveled. But I can't use 2 seconds. So if I wanted to find the distance away, so velocity is equal to distance divided by time, I can rearrange that to say that velocity multiplied by time is equal to distance. If I said that the time taken was 2 seconds, I would mistakenly say that the distance was 600 meters. Because it's not 600 meters away. The echo has traveled for 600 meters, but the fish itself is 300 meters away. So if you get a question about a ping and an echo, be it from a sonar device to a fish or a mouth to a wall, divide the time by 2, giving me my velocity as 300, my distance as 300 times 1, making 300 meters. This makes sense because if a ping takes 1 second to travel and it travels at 300 meters per second, then after one of these seconds, it will have traveled 300 meters. After another one of those seconds, it would have traveled another 300 meters. So hopefully that would have cleared up the confusion. Threw me a little bit because I didn't RTFQ when I was getting these things ready. Obviously not prepared enough. Thank you very much. Have a lovely day. Yeah. Oh, no. Yep, okay, I'm still recording because my mouse isn't working. Just that casual. I wonder if I can edit these things. How do I... Okay, thank you. There we go. Okay, we'll delete this. Yes, stop recording.